There is a body of water in northern Canada so large that early European explorers thought they had finally found the Pacific Ocean. It stretches nearly 1,000,000 square kilometers. It is surrounded by some of the most desolate, wind-punished landscape on Earth. Polar bears roam its shores. Beluga whales move through its shallows in summer. Inuit hunters have navigated its frozen surface for thousands of years. And beneath all of it, sealed under rock and ice and geological time, something has been sitting there since before the first human being ever walked across the land bridge from Asia. Scientists have known about it for decades. The data has been collected, studied, argued over, and quietly filed away in academic journals that most people will never read. Geologists call it one of the most unusual features on the planet. Physicists have built entire theories around it. And yet, almost nobody outside of specialized academic circles has ever heard of it. This is the story of what lies beneath Hudson Bay. It is a story about the deepest forces that shape our world. It is a story about the age of the Earth itself. It is a story about mass extinction, about the birth and death of entire continents, about gravity anomalies so strange that they baffled researchers for a generation. And it is a story about why this particular patch of ancient Canadian rock may be one of the most geologically significant places on the surface of the entire planet. If you find this kind of content worth your time, subscribe right now. Every week, we go into the places that history books skip, the geological puzzles that universities argue about, the sealed chapters of earth science that barely make the news. Hit subscribe before we go any further, because this one is going to take a while. Now, let us begin at the beginning, and when it comes to Hudson Bay, the beginning is a very, very long time ago. To understand what is sealed beneath Hudson Bay, you first have to understand what Hudson Bay actually is, not in the casual geographic sense that most Canadians learn in school, where it is simply a large body of cold water in the northern part of the country. You have to understand it the way a geologist understands it, which means understanding it across timescales that are genuinely difficult for the human mind to process. Hudson Bay sits in the middle of what geologists call the Canadian Shield. The Shield is one of the oldest exposed rock formations on the surface of the Earth. Parts of it are more than 4 billion years old. To put that in perspective, the dinosaurs went extinct 66 million years ago. The earliest complex life appeared in the oceans about 500 million years ago. The Canadian Shield is 8 times older than that. It formed during what geologists call the Precambrian era, and it has been sitting in essentially the same place ever since, slowly worn down by billions of years of erosion, glaciation, and the relentless pressure of geological time. The rock beneath Hudson Bay is part of this ancient shield, but something about it is different from the surrounding Canadian Shield in ways that took scientists many decades to fully appreciate. In the 1960s and 1970s, as satellite technology and gravitational measurement equipment became increasingly sophisticated, researchers began noticing something strange about Hudson Bay. The gravitational field over the bay was weaker than it should have been. Not dramatically weaker, not in any way that you would notice if you were standing on the shore, but measurably, persistently, undeniably weaker than the models predicted it should be. Gravity, as most people understand it in a basic way, pulls things toward the center of the Earth, but gravity is not perfectly uniform across the planet's surface. The mass of the rock beneath your feet affects how strongly gravity pulls at you. Dense, heavy rock beneath the surface means stronger gravitational pull. Less dense rock, or regions where rock has been removed or compressed, means slightly weaker pull. Scientists measure these variations using instruments called gravimeters, and by the time they had mapped the gravitational field across North America in detail, Hudson Bay had become one of the most peculiar anomalies on the continent. The question of why gravity was lower over Hudson Bay generated decades of scientific debate. Two main theories emerged, and both of them, in different ways, point to something extraordinary about what happened to this region of the Earth's surface. The first theory involves what geologists call post-glacial rebound. During the last ice age, which ended roughly 12,000 years ago, Hudson Bay was buried under an absolutely enormous sheet of ice. The Laurentide ice sheet, which covered most of northern North America, was at its maximum extent, perhaps 3 kilometers thick over the Hudson Bay region. 3 kilometers of ice represents an almost incomprehensible weight pressing down on the Earth's crust. The crust is not rigid in the way we often imagine it. Over geological timescales, it behaves more like a very slow-moving fluid. Press down on it hard enough for long enough, and it will deform. The weight of the Laurentide ice sheet actually pushed the crust down, compressing it into the mantle beneath. When the ice melted, that weight was removed, and the crust began to rebound. It has been rebounding ever since. The land around Hudson Bay is still rising at a rate of about 1 centimeter per year in some places. This ongoing rebound means that the crust is still less dense than it would normally be, because the rock and the mantle material beneath it have not fully recovered from being compressed, and less dense crust means weaker gravitational pull. This explanation, known as the post-glacial rebound theory, accounts for a significant portion of the gravitational anomaly over Hudson Bay. Scientists were largely satisfied with it for many years. The math worked reasonably well. The rates of rebound matched what the models predicted. It was a clean, elegant explanation for a genuinely unusual phenomenon, and it fit neatly into the broader story of how the Earth's crust responds to the loading and unloading of massive ice sheets. But then researchers started noticing that the rebound theory did not account for all of the anomaly. Even after correcting for the effects of the ice age, even after running the numbers as carefully as they could with the best models available, there was still a residual gravitational deficit over Hudson Bay that the ice sheet alone could not explain. Something else was going on beneath the surface. The second theory, and the one that has generated far more controversy and fascination in the geological community, reaches much further back in time. It reaches back not 12,000 years to the end of the last ice age, but hundreds of millions of years, to a period in the Earth's history when the continents themselves were arranged in a completely different configuration. To understand this second theory, you have to understand something about how the Earth's interior actually works. The outermost layer of the Earth, the crust, is not a single continuous shell. It is broken into large pieces called tectonic plates, which float on the much hotter, partially molten layer beneath them called the mantle. The mantle extends from the base of the crust all the way down to the outer core, a distance of roughly 2,900 kilometers. The mantle is not liquid exactly. It is a solid rock that, over time scales of millions of years, flows and convects like an extremely slow and viscous fluid. Within the mantle, there are regions of rock that are hotter than their surroundings, and regions that are cooler. The hot regions rise toward the surface. The cool regions sink. This convection is part of what drives the movement of tectonic plates at the surface. And within this churning, convecting mantle, there are also regions of unusually dense, cold material that sit near the base of the mantle and move only very slowly. These dense regions are called mantle downwellings, or in some contexts, cold mantle anomalies. And researchers discovered something remarkable when they began mapping them beneath North America. Directly beneath Hudson Bay, extending deep into the mantle, there appears to be a region of unusually dense, cold rock. This cold, dense material pulls the overlying crust slightly downward and reduces the local gravitational field in specific ways that the post-glacial rebound alone cannot explain. Where did this dense cold region come from? The answer to that question takes us back to one of the most dramatic events in the history of the North American continent, an event so ancient that it predates all complex life on Earth, an event that left a scar in the planet's interior that is still visible today if you know what to look for. The Canadian Shield, the ancient rock that surrounds and underlies Hudson Bay, is not a single uniform geological unit. If you could peel away the thin veneer of surface rock and look at the deeper structure beneath, you would find the traces of ancient mountain ranges that were once as tall as the Himalayas, ancient ocean basins that no longer exist, ancient volcanic arcs, and the remnants of tectonic collisions that took place billions of years before any plant ever grew on land. One of the most important of these ancient features is something called the Trans-Hudson origin. The word origin simply means a mountain-building event, a period when tectonic plates collide and the crust buckles upward into mountain ranges. The Trans-Hudson origin happened roughly 1.9 to 1.8 billion years ago, and it was one of the largest mountain-building events in the history of the planet. When it was over, the colliding plates had welded together to form a single massive continent. The suture zone, the line where the ancient plates joined, runs directly beneath and around Hudson Bay. Think about what that means. Hudson Bay is not sitting randomly on top of the Canadian Shield. It is sitting on top of one of the oldest and most fundamental geological boundaries in North America. The bay itself may occupy the region it does precisely because of what happened along this ancient suture zone nearly 2 billion years ago. The cold, dense material that researchers detect in the mantle beneath Hudson Bay may be the remnant root of those ancient mountains. When continents collide and mountains form, the crust thickens dramatically. Below the visible mountains, a deep root of cold, dense crustal and lithospheric material extends downward into the mantle. When the mountains eventually erode away, over hundreds of millions of years, the root can persist long after the peaks above it have completely disappeared. It is possible that what sits beneath Hudson Bay is precisely this kind of fossil mountain root, a remnant of the Trans-Hudson collision preserved in the Earth's interior for nearly 2 billion years. If that is true, it means the gravitational anomaly over Hudson Bay is not just a curiosity. It is a window into the deepest geological history of the continent. It is evidence of events that happened long before the first cell ever divided, long before oxygen accumulated in the atmosphere, long before any complex organism drew a breath. The thing that is sealed beneath Hudson Bay has been there since the world was less than half its current age. But that is not even the most dramatic part of this story, because buried within the geological record of the Hudson Bay region, layered into the ancient rock and the sediments that have accumulated over billions of years, there is evidence of something else, something that happened on a very different timescale, something that left marks on the surface as well as deep underground, something that wiped out an enormous proportion of life on Earth and rewrote the biological history of the planet. To understand that part of the story, we need to go back roughly 450 million years to a period called the Ordovician, when the oceans were full of strange and ancient life, and the continents looked nothing like they do today. The Ordovician period is one of the least discussed chapters of Earth's history, and that is a shame, because it contains one of the most devastating mass extinction events in the planet's entire fossil record. Not the most famous one, that would be the end Cretaceous extinction that killed the dinosaurs. Not the largest one, that would be the end Permian extinction, roughly 252 million years ago, which killed perhaps 96% of all marine species. The Ordovician extinction, which happened at the end of the Ordovician period roughly 443 million years ago, was the second largest mass extinction event in the history of complex life on Earth. It killed approximately 85% of all marine species. 85%. To appreciate what that number means, consider the oceans of the Ordovician period. They were not the empty, algae-rich seas of the early Precambrian. By 450 million years ago, the oceans had been filling with complex animal life for roughly 100 million years. There were trilobites in extraordinary variety, dozens of families, hundreds of species, filling every available ecological niche. There were brachiopods, creatures superficially resembling clams, but entirely unrelated to them, coating the seafloors in vast colonies. There were cephalopods, the ancestors of modern squid and nautiluses, some of them enormous and voracious predators. There were echinoderms, relatives of modern sea urchins and starfish, in forms that no longer exist today. There were graptolites, strange colonial organisms that drifted through the water, column in their millions. The Ordovician oceans were complex, diverse, and teeming with life. And then, at the end of the Ordovician period, most of it died. The cause of the Ordovician extinction has been debated for decades. The leading hypothesis involves a dramatic cooling of the global climate, driven by the formation of a massive ice sheet over what is now the Sahara Desert. In the Ordovician, the supercontinent called Gondwana sat over the South Pole, and conditions cooled dramatically, enough to produce glaciation on a continental scale. The glaciation locked up enormous amounts of water, dropping sea levels dramatically. The combination of cooling temperatures, dropping sea levels, and the associated changes in ocean chemistry devastated the rich marine ecosystems of the Ordovician. But in recent decades, a competing and more dramatic hypothesis has been gaining traction among researchers. It involves not glaciation, but radiation. Specifically, a gamma-ray burst. A gamma-ray burst is the most energetic explosion in the known universe. They occur when massive stars collapse into black holes, or when neutron stars collide, and the energy released in a fraction of a second can outshine an entire galaxy. They produce focused beams of intense gamma radiation, and if one of those beams were to strike the Earth, the consequences would be catastrophic. A gamma-ray burst powerful enough and close enough would strip away the ozone layer on the side of the planet facing the burst. With the ozone layer gone, ultraviolet radiation from the sun would reach the surface at lethal levels. The UV radiation would devastate surface life and shallow marine life. It would also trigger a chain of chemical reactions in the atmosphere that would produce nitric oxide compounds, which would persist for years, further damaging the ozone layer and causing a prolonged period of atmospheric disruption. Some researchers have proposed that the Ordovician mass extinction was triggered or significantly worsened by exactly such an event, a nearby gamma-ray burst within a few thousand light years of the solar system, striking the Earth at the end of the Ordovician and setting off the chain of events that killed 85% of marine life. The evidence for this is indirect. You cannot find a smoking gun in the geological record that says with certainty a gamma-ray burst hit the Earth 443 million years ago. But the pattern of extinction in the Ordovician, particularly the way it appears to have preferentially devastated life in shallow water habitats exposed to more intense radiation, is consistent with what you would expect from a catastrophic UV pulse, and Hudson Bay enters this story in a specific and remarkable way, because the sedimentary rocks that were laid down in the Hudson Bay region during and after the Ordovician extinction are among the best preserved records of that event anywhere on Earth. The ancient, geologically stable nature of the Canadian Shield means that those rocks have not been subjected to the intense deformation and metamorphism that has obscured the Ordovician record in many other parts of the world. The Hudson Bay region is a natural archive of one of the greatest catastrophes in the history of life on Earth. When geologists drill cores from the sedimentary rocks of the Hudson Bay lowlands, they pull up samples that tell the story of the Ordovician world directly. The fossils in those rocks change dramatically across the extinction boundary. One layer is full of diverse, thriving Ordovician communities. The next is nearly empty. The transition is abrupt, and in the rocks deposited in the immediate aftermath of the extinction, there are chemical signatures that researchers are still arguing about, signals that might represent the fingerprints of the catastrophe that caused the extinction, whatever it ultimately was. Below those Ordovician sediments, deeper in the drill cores, the rocks become older and different in character. These are the ancient crystalline rocks of the shield itself, the ones that formed during and after the trans-Hudson origin nearly 2 billion years ago. And these rocks tell a completely different kind of story, one that reaches even further back in time, to a period when the Earth itself was a fundamentally different world. The Precambrian era is not a single period of geological time. It is a vast expanse of time that covers roughly 88% of the entire history of the Earth. From the formation of the planet approximately 4.5 billion years ago to the beginning of the Cambrian period 541 million years ago, every second of that enormous span is technically Precambrian. Within that expanse, geologists have identified broad subdivisions: the Hadean, the Archean, and the Proterozoic, each representing distinct phases in the development of the planet and the life upon it. The rocks of the Canadian Shield span most of this entire history. The oldest rocks in the region, found near the shore of Hudson Bay in northern Quebec and Ontario, date to more than 3 billion years ago. They formed during the Archean eon, when the Earth's crust was thinner and more geologically active than it is today, when volcanic activity was more intense and widespread, when the oceans were warmer and had a different chemical composition, and when the atmosphere contained almost no oxygen. That last point is worth dwelling on. For most of the Earth's history, oxygen was not a significant component of the atmosphere. The early atmosphere was dominated by nitrogen, carbon dioxide, methane, and other gases produced by volcanic activity. It was not until approximately 2.4 billion years ago, during an event geologists call the Great Oxidation Event, that free oxygen began accumulating in the atmosphere in significant quantities. The cause of the Great Oxidation Event was biological. A group of microorganisms called cyanobacteria, which had evolved the ability to perform photosynthesis and produce oxygen as a byproduct, became so abundant in the ancient oceans that the oxygen they generated began to overwhelm the chemical reactions that had been removing it from the atmosphere. Oxygen levels rose dramatically over a period of millions of years, transforming the chemistry of the atmosphere, the oceans, and the surface rocks of the planet. This transformation was not gentle. To the microorganisms that had evolved in an oxygen-free world, the sudden accumulation of oxygen in the atmosphere and oceans was catastrophic. Oxygen is a highly reactive element, and for life that had evolved in its absence, it was essentially a poison. The Great Oxidation Event caused one of the earliest and most comprehensive mass extinctions in the history of life on Earth, a die-off of anaerobic microorganisms so vast and complete that it dwarfs anything that happened later, including the end Permian extinction that killed the dinosaurs. The rocks of the Canadian Shield contain the chemical signatures of this transformation. In the ancient iron formations, the banded sequences of iron-rich and silica-rich rock that were deposited in the Precambrian oceans, you can read the story of the Great Oxidation Event directly. As oxygen became available in the ocean water, it combined with dissolved iron to form iron oxides, which precipitated out of the water and settled to the sea floor. The result was the banded iron formations, some of the most economically important rock formations on Earth because they are the source of most of the world's iron ore, and also some of the most scientifically significant because they preserve a detailed chemical record of the changing ocean chemistry during one of the most important transitions in the history of the planet. The Hudson Bay region contains extensive banded iron formations. Some of the most significant iron ore deposits in Canada are found in the rocks that surround the bay, in Quebec and Ontario and Manitoba. These deposits are the direct legacy of events that happened roughly 2.5 to 2.0 billion years ago, when oxygen was transforming the chemistry of the ancient oceans. And beneath those iron formations, deeper still in the geological column, are the oldest rocks of all, the Archean basement, the foundation upon which everything else was built. These rocks formed in the first half of the Earth's history, in an era so remote that the geological processes that shaped them were fundamentally different from the processes that shape the Earth today. The Archean Earth was hotter internally than the modern Earth. The mantle convected more vigorously. Volcanic activity was more intense. The crust was thinner and more unstable. What we would recognize as modern plate tectonics, with large, rigid plates moving slowly and predictably across the surface, may not yet have existed in the Archean in the form we know it today. Instead, the crust may have been broken into many smaller, more unstable pieces that interacted in more complex and chaotic ways. In this vigorous geological environment, the ancient crustal fragments that would eventually become the Canadian Shield were assembled. Volcanic islands formed and were swept into collision with one another. Chunks of oceanic crust were thrust beneath continental fragments and pushed deep into the mantle. Ancient mountain ranges rose and eroded, and gradually, over hundreds of millions of years, larger and more stable continental masses began to form from the assembled fragments. The process by which these ancient continental fragments were welded together is preserved in the structure of the Canadian Shield itself. Geologists can map the boundaries between the ancient crustal blocks, called cratons, and trace the suture zones where they were joined. Each suture zone represents an ancient collision, an event when two separate pieces of crust were forced together and locked into a single mass. Hudson Bay sits at the center of one of the most important of these ancient collisions, the Superior Craton, one of the largest and oldest cratons in North America, stretching from northern Ontario westward into Manitoba, forms the eastern and southern margin of the Hudson Bay region. The Churchill Province, another ancient block, forms the western and northern margins, and the Trans-Hudson Origin, the massive mountain building event that happened 1.9 to 1.8 billion years ago, is the record of the collision between these two ancient crustal blocks. The Trans-Hudson collision was one of the most significant tectonic events in the history of North America. It was not a quick event. It played out over tens of millions of years, as the ancient ocean that had separated the Superior Craton from the Churchill Province was gradually subducted, as the two continental masses approached each other, and as the final collision thrust rock upward into mountains of Himalayan scale. The trace of that ancient ocean, the Manikawan Ocean, as geologists call it, is preserved in the rock record of the Hudson Bay region. Ophiolites, fragments of ancient oceanic crust that were scraped off the subducting plate and preserved in the collision zone, can be found in the rocks of northern Manitoba and Saskatchewan. They are the remnants of an ocean floor that no longer exists, that was consumed by subduction and collision nearly 2 billion years ago. But pieces of it survived, caught in the suture zone and carried to the surface over geological time. These ophiolites are scientifically extraordinary. They are among the oldest preserved examples of oceanic crust anywhere on Earth. They tell us that plate tectonics, in a recognizable form, was already operating nearly 2 billion years ago. The processes that shape the modern world, the subduction of oceanic crust beneath continental margins, the collision of continents, the formation of mountain ranges, were already at work in the Proterozoic era. And the root of those ancient trans-Hudson mountains, compressed deep into the mantle by the weight of the colliding crustal masses, is likely still down there beneath Hudson Bay, a remnant of one of the greatest tectonic events in Canadian geological history, preserved in the cold mantle beneath the bay for nearly 2 billion years. But the story of what is sealed beneath Hudson Bay does not stop with the rocks and the ancient tectonics, because superimposed on top of all this ancient geological history is another layer of evidence, a layer laid down far more recently in geological terms, that speaks to catastrophic and dramatic events on a completely different timescale. Roughly 1.85 billion years ago, something struck the Earth in the region of what is now northern Ontario. Something large, something moving at an enormous velocity. The resulting impact was one of the largest in the known geological record of North America. The crater it produced, known as the Sudbury Basin, is roughly 130 kilometers across and is one of the largest and oldest confirmed impact craters on Earth. The Sudbury impact was not related to Hudson Bay directly, but it is part of the broader geological context of the Canadian Shield, and it speaks to the reality that the ancient cratons of North America have been subjected to cosmic bombardment repeatedly over their multi-billion-year history. The period roughly 4 billion to 3.8 billion years ago, known as the Late Heavy Bombardment, was a time when the inner solar system was subjected to an intense rain of asteroid and comet impacts, as leftover debris from the formation of the solar system was swept up by the planets. The lunar highlands are covered in impact craters from this period, and the Earth, with its much larger gravitational field, would have been struck far more frequently than the Moon. None of those ancient impacts are preserved at the surface of the Earth today. The geological processes of erosion, volcanism, and crustal recycling have long since erased the craters from the late heavy bombardment. But the Canadian Shield, with its ancient and relatively stable geology, preserves impact structures from much more recent cosmic bombardments. Sudbury, at 1.85 billion years. The Manicouagan structure in Quebec at approximately 215 million years. The Clearwater Lakes in Quebec, a double impact crater from roughly 290 million years ago. The Canadian Shield is, in a very real sense, a record of the solar system's ongoing bombardment of the Earth. And here is where the story deepens in a particularly fascinating way, because some researchers have proposed that the structural basin occupied by Hudson Bay itself may reflect, at least in part, the influence of ancient impact events on the overlying crustal structure. The bay is roughly oval in shape, and while its current form is largely the result of glacial erosion and post-glacial isostatic adjustment, some geologists have wondered whether the underlying crustal weakness that made this region susceptible to glacial erosion might itself have been influenced by ancient impact events or by the complex tectonic history of the trans-Hudson suture zone. This idea is controversial and not broadly accepted by the mainstream geological community. The consensus view is that Hudson Bay's shape and location are primarily the result of glacial processes operating on a crustal region that was already relatively low-lying because of the ancient tectonic history. But the question is not entirely closed, and it illustrates how complex and multi-layered the geological history of the Hudson Bay region truly is, because you are not dealing with a single event or a single process when you try to understand what lies beneath Hudson Bay. You are dealing with layer upon layer of geological history, each layer preserving the record of a different era, a different set of processes, a different chapter in the story of the Earth, the ancient Archean basement, the banded iron formations of the Great Oxidation Event, the Trans-Hudson Suture Zone and its deep mantle route, the Ordovician sediments with their record of mass extinction, the Paleozoic carbonates and shales deposited in shallow tropical seas when the Canadian Shield sat at a very different latitude than it does today, and over all of it, the glacial record of the last 2 million years, the most recent and in some ways the most dramatic chapter in the story of this particular piece of ground. It is that glacial record that brings us to the most immediate and visceral aspect of what lies beneath Hudson Bay, because the ice did not simply sit on top of the ancient rocks and then melt away. It transformed them. It carved them. It pressed them down into the mantle, and when it melted, it left behind a landscape that is still recovering, still rising, still adjusting to the removal of a weight that had been pressing on it for tens of thousands of years. The last glacial maximum occurred approximately 20,000 years ago. At that point, the Laurentide ice sheet covered virtually all of Canada and extended well into the northern United States. Hudson Bay did not exist as a body of water at the last glacial maximum. It was buried under kilometers of ice, pressed down, frozen, locked under a weight of accumulated snow, and ice that had been building for tens of thousands of years. The center of the Laurentide ice sheet, the region where the ice was thickest and where it persisted the longest, was over Hudson Bay. This was not coincidence. The geography of the Hudson Bay lowlands, the relatively flat terrain surrounding the bay, the moisture supply from the bay itself during warmer periods when the bay was ice-free, made it an ideal nucleation point for ice sheet formation. The ice built up here first and melted here last. At its maximum thickness, the ice sheet over Hudson Bay may have been as much as 3 to 4 kilometers thick. 4 kilometers of ice, a column of ice 4 times taller than the CN Tower in Toronto, and pressing that column of ice across the entire surface of Hudson Bay and the surrounding lowlands, across an area of nearly 1 million square kilometers. The weight of that ice pressed the crust down by several hundred meters. The underlying mantle, displaced by the weight, flowed outward and away from the ice sheet, causing a subtle bulge around the margins of the glaciated area. This forebulge, as it is called, affected regions well beyond the ice sheet margin. When the ice melted, the weight was removed. But the mantle does not spring back instantly. It is too viscous, too slow-moving. The rebound of the crust happened and continues to happen at the pace of the mantle's relaxation, which is measured in centuries and millennia. 12,000 years after the ice sheet began its final retreat, the land around Hudson Bay is still rising. The bay itself is getting shallower as the floor of it rises. In geological terms, this is happening almost instantaneously. In human terms, it is so slow as to be invisible without precise measurement instruments. The fact that the crust is still rebounding tells us something important about the mantle beneath Hudson Bay. The rate of rebound depends on the viscosity of the mantle, and the viscosity in turn depends on temperature and composition. The rebound data from Hudson Bay has been used by scientists to probe the structure and composition of the mantle beneath the region, providing another line of evidence about what is sealed down there below the bay. The results from this analysis are consistent with the picture that emerges from the gravity data and the seismic tomography studies. There is something unusual about the mantle beneath Hudson Bay, something cold, dense, and ancient, something that has been sitting there, affecting the gravitational field and the thermal structure of the crust above it for an enormous span of geological time, And it is here that the story of Hudson Bay connects to one of the most profound questions in modern geoscience, the question of how the Earth's interior preserves the record of ancient surface processes, because the cold, dense route beneath Hudson Bay is not just a geological curiosity. It is, if the interpretations are correct, a direct window into the deep structure of the ancient supercontinent that existed nearly 2 billion years ago. The mountains that formed during the trans-Hudson origin have long since eroded away. The ocean that separated the Superior Craton from the Churchill province is gone, subducted into the mantle without a trace at the surface. But the root of those mountains, compressed into the cold, dense mantle beneath Hudson Bay, may still be there, a fossil of a world that existed before complex life, before oxygen in the atmosphere, before the continents took their current configuration. To truly appreciate the significance of what lies beneath Hudson Bay, you have to understand what geophysicists mean when they talk about seismic tomography. It is the technique that has done more than any other to reveal the hidden structure of the Earth's interior, and it has produced some of the most striking images ever generated of what lies beneath the surface of the planet. Seismic tomography works by using earthquake waves. When an earthquake occurs, it sends seismic waves radiating outward through the Earth in all directions. These waves travel through the planet's interior, and as they do, their speed varies depending on the properties of the material they are passing through. Hotter rock slows seismic waves down. Colder, denser rock speeds them up. By recording these waves at seismograph stations around the world and analyzing the variations in their travel times, geophysicists can reconstruct a three-dimensional image of the Earth's interior, similar in principle to the way a CT scan creates a three-dimensional image of the inside of a human body. The technique has been refined over decades, and modern seismic tomography can resolve features in the mantle with a spatial resolution of tens to hundreds of kilometers. It is not perfect. It cannot show you every detail, but it can reveal the broad structure of the mantle beneath major geological features, and what it shows beneath Hudson Bay is striking. Beneath the Hudson Bay region, seismic tomography reveals a large, coherent region of fast velocity material in the upper mantle. Fast velocity means the seismic waves are moving more quickly through this material than they would through average mantle rock. Fast velocity anomalies in the mantle typically represent material that is colder and denser than its surroundings. Cold, because it has not been heated by the mantle. Convection that circulates heat from the Earth's interior toward the surface. Dense because cold rock contracts and becomes denser than the surrounding warmer material. This fast velocity region beneath Hudson Bay is large. It extends from the base of the crust, which in the stable cratons of the Canadian Shield is thick, perhaps 40 to 50 kilometers, all the way down to depths of 200 kilometers or more in some interpretations of the tomography data. It is a deep keel of cold, ancient lithospheric material sitting beneath the bay and the surrounding shield rocks, and it has almost certainly been there in some form since the trans-Hudson origin welded the Superior and Churchill cratons together nearly 2 billion years ago. The lithospheric keel of an ancient craton is one of the most distinctive features in the seismic tomography of the stable continental interiors. The old cold cratons of the world, the Kaapval craton of southern Africa, the Pilbara and Yilgarn cratons of Western Australia, the Kola craton of northern Europe, all show similar thick lithospheric roots in seismic tomography. These roots are the reason the ancient cratons have survived billions of years of geological activity, while the surrounding younger crust has been repeatedly deformed, subducted, and recycled. The cold, buoyant keel acts as a stabilizing anchor, resisting the drag of mantle, convection that would otherwise erode and destabilize the overlying crust. The Hudson Bay region sits on one of these ancient, stable, lithospheric keels, and the keel itself, the cold, dense root of ancient lithosphere preserved from the trans-Hudson collision, is what the gravity data and the seismic tomography are detecting. It is one of the oldest coherent pieces of lithosphere in North America, and it has been sitting beneath what is now Hudson Bay, locked in cold stability for nearly 2 billion years. But the story does not stay comfortably in the deep past, because what lies beneath Hudson Bay also intersects with much more recent geological history in ways that are directly relevant to the world we live in today. Specifically, it intersects with the question of how the Earth's climate system operates over long timescales, and how the geological character of the Hudson Bay region has influenced and been influenced by the great glaciations of the past 2 million years. The Quaternary period, which spans the last approximately 2.6 million years of Earth's history, has been characterized by repeated cycles of glaciation and deglaciation. During glacial maxima, ice sheets expand to cover large portions of the high-latitude continental areas of the northern hemisphere. During interglacials, like the one we are currently living in, the ice sheets retreat and the formerly glaciated areas slowly recover. The Hudson Bay region has been affected by every major glacial cycle of the Quaternary. Ice has expanded and contracted over it again and again. Each cycle of glaciation has deposited sediments, carved rock, and left its mark on the landscape. And because the bedrock beneath Hudson Bay is ancient and hard, it has preserved the record of these glacial cycles in ways that softer, younger rock would not. Understanding the glacial history of the Hudson Bay region is one of the central challenges of Canadian quaternary geology, and it is more complicated than it might initially appear, because Hudson Bay is not simply a passive recipient of glacial ice. Its geography, its position in the heart of the northern Canadian landmass, its configuration of shallow water and surrounding lowlands, make it an active participant in the glacial system. During glaciations, Hudson Bay is the center of the ice sheet. During deglaciations, as the ice melts, Hudson Bay becomes a proglacial lake, a body of cold meltwater dammed by the remnant ice sheet. And as the deglaciation progresses and the ice retreats, Hudson Bay eventually opens to the sea through Hudson Strait, becoming a partially marine environment before the post-glacial rebound raises the surrounding land enough to restrict the marine connection. Each of these phases, glacial, proglacial, marine, and the current brackish marine phase, has left its own distinct signature in the sediments on the floor of Hudson Bay. The sediment record of the bay is therefore a detailed archive of climate and environmental change over the past 12,000 years, and drilling and sampling that sediment record is one of the most active areas of paleoclimate research in Canada. The sediment cores from Hudson Bay contain pollen, the preserved pollen grains of ancient plants that tell us about the vegetation that existed around the bay at different times. They contain microfossils, tiny shells of microscopic marine organisms that tell us about the temperature and salinity of the water. They contain organic carbon, the preserved remains of plants and animals that tell us about the productivity of the bay's ecosystem. And in the deepest cores, below the Holocene sediments, there are glimpses of earlier glacial and interglacial periods, earlier chapters in the ongoing story of climate change and ecosystem response. The data from these cores has transformed our understanding of how the Hudson Bay region responded to the end of the last ice age. The deglaciation of Hudson Bay was not a simple, gradual process. It was marked by abrupt changes, sudden reorganizations of the meltwater drainage patterns, and at least one catastrophic event that had global consequences. That event is known as the Lake Agassiz outburst flood. Lake Agassiz was the largest proglacial lake in North America's history, Formed as the Laurentide ice sheet retreated from its southern and eastern margins, it eventually covered a vast area of central Canada, parts of what are now Manitoba, Saskatchewan, Ontario, and the Dakotas. At its maximum extent, Lake Agassiz was larger than all of the modern Great Lakes combined. Its shorelines are still visible in the landscape of the Canadian prairies, where ancient beach ridges mark the former margins of the lake. As the ice sheet continued to retreat northward, it eventually uncovered a drainage route from Lake Agassiz into Hudson Bay. And when that route opened, an enormous volume of cold, fresh water was discharged into Hudson Bay and from there into the North Atlantic Ocean. The volume of fresh water released in this event was staggering. Estimates vary, but some researchers suggest that the Lake Agassiz outburst may have discharged as much as 163,000 cubic kilometers of fresh water into the ocean in a geologically brief period. The consequences of injecting that much cold fresh water into the North Atlantic were severe and far-reaching. The North Atlantic thermohaline circulation, the system of ocean currents driven by the sinking of cold, salty water in the high-latitude North Atlantic, is extremely sensitive to freshwater input. Fresh water is less dense than salt water, and large additions of fresh water can disrupt the sinking of dense salt water that drives the circulation. When the circulation slows or shuts down, the transport of heat from the tropics to the high-latitude North Atlantic is reduced, and temperatures in the North Atlantic region cool dramatically. The Lake Agassiz outburst flood is thought by many researchers to have triggered or substantially contributed to a climate event known as the Younger Dryas, a rapid cooling of the northern hemisphere that lasted approximately 200 years and interrupted the warming trend of the post-glacial period. During the Younger Dryas, temperatures in the North Atlantic region dropped by as much as 10 degrees Celsius. Glaciers re-advanced in many areas. The warming trend that had been progressively melting the ice sheets went into temporary reverse. Hudson Bay was both the conduit for the Lake Agassiz outburst and one of the primary recipients of its consequences. The influx of cold fresh water into the bay transformed its water chemistry and ecology, and the subsequent Younger Dryas cooling caused partial reglaciation of the Hudson Bay region, adding another layer of complexity to the glacial record preserved in the sediments and the bedrock. The Younger Dryas ended approximately 11,700 years ago, as abruptly as it had begun. Within a few decades, temperatures in the North Atlantic region rose sharply back toward the warm interglacial values that had characterized the early deglaciation. The speed of this transition, which appears to have happened in as little as 1 to 3 decades based on ice core records from Greenland, is one of the most remarkable and puzzling features of the climate record of the last ice age. After the Younger Dryas, the warming continued, and the last remnants of the Laurentide ice sheet over Hudson Bay melted. The final collapse of the ice dome over Hudson Bay is thought to have occurred approximately 8,000 to 7,000 years ago. As the ice retreated and the bay opened to marine waters, an entirely new ecological system came into being. Marine mammals, particularly beluga whales and ringed seals, colonized the bay. Arctic birds began nesting along its shores. And gradually, over subsequent millennia, the first human inhabitants of the region, the ancestors of the Cree and Ojibwe peoples on the southern shores, and the Inuit on the northern coast, developed deep and sophisticated relationships with the bay and its resources. But beneath all of this recent ecological and cultural history, the ancient geology persists. The rocks that were being formed during the trans-Hudson origin are still there. The mantle keel of cold, dense, ancient lithosphere is still there. The gravitational anomaly is still measurable. The rebound is still occurring. The earth beneath Hudson Bay is still in motion, still adjusting, still slowly recovering from the last great glaciation, even as the climate system above it begins to show signs of a very different kind of change. And here is where the story of what lies beneath Hudson Bay connects to the present day in a way that has significant and practical consequences. Because the ongoing post-glacial rebound of the Hudson Bay region is not just a geological curiosity. It affects sea level. It affects the hydrology of the bay and the surrounding rivers. It affects the ecology of the coastal wetlands and the marine environment. And as the climate continues to warm and the remaining ice in the Arctic region continues to melt, the dynamics of isostatic adjustment around Hudson Bay are becoming an increasingly important factor in understanding how the region will change over the coming centuries. The warming of the climate in the Hudson Bay region is not hypothetical. It is already well underway. The Hudson Bay region is warming at a rate approximately twice the global average, a pattern that is consistent with what climate models predict for the high-latitude regions of the northern hemisphere, where the loss of sea ice creates a feedback loop that accelerates warming. The sea ice season on Hudson Bay has shortened dramatically in recent decades. The period of open water has extended. The ecological consequences for polar bears, for seals, for beluga whales, for seabirds are already visible and well documented. But the geological response to this warming is less immediately visible, though no less significant. As the climate warms, the permafrost that underlies vast areas of the Hudson Bay, lowlands and the surrounding regions is beginning to thaw. And in the permafrost, enormous quantities of organic carbon, the frozen remains of plants and animals that accumulated in the cold soils over thousands of years, are locked away. When the permafrost thaws, that organic carbon becomes available to decompose, releasing carbon dioxide and methane into the atmosphere and creating a powerful feedback that could significantly accelerate warming. The Hudson Bay lowlands are one of the largest peatland complexes in the world. The peat, which is partially decomposed. Organic matter accumulated in waterlogged conditions over thousands of years since the last glaciation represents an enormous reservoir of carbon. Estimates suggest that the Hudson Bay lowlands store several billion tons of carbon in their peat deposits. If climate warming triggers widespread permafrost thaw and peat decomposition in this region, the resulting greenhouse gas emissions could be substantial on a global scale. This is the most immediate and pressing connection between what lies beneath Hudson Bay and the world we inhabit today. The geological history of the region, the ancient rocks, the glacial legacy, the post-glacial accumulation of peat and carbon in the low-lying terrain around the bay has created conditions that make the Hudson Bay region one of the most sensitive and consequential places on Earth in terms of the global carbon cycle. What happens here in the coming decades will matter not just for the communities that live around the bay, but for the global climate system as a whole. The human history of the Hudson Bay region is as layered and complex as the geological record beneath it. And just as the geological history reaches back into deep time, the human story of Hudson Bay reaches back much further than most Canadians are taught in school. The conventional narrative tends to emphasize the arrival of European explorers and the establishment of the fur trade, which are undeniably dramatic chapters in the story of the bay. But human beings have been living around Hudson Bay for thousands of years before any European ship ever entered its waters, and the story of those peoples and their relationship with this extraordinary environment is one of the most remarkable chapters in the broader human story of North America. The first human inhabitants of the Hudson Bay region were not a single people. They were the descendants of successive waves of migration and population movement across the North American continent, each wave adapting to the specific conditions of the Hudson Bay environment in different ways, developing different technologies, different social structures, and different relationships with the landscape and its resources. The oldest evidence of human presence in the broader Hudson Bay region dates to approximately 8,000 years ago, shortly after the final retreat of the Laurentide ice sheet from the bay's shore. These earliest inhabitants were part of what archaeologists call the Shield Archaic cultural tradition, a broad complex of cultures spread across the Canadian Shield in the millennia following deglaciation. They lived by hunting caribou, fishing, and gathering plant foods, following the seasonal movements of animal populations and adapting to the challenging conditions of the post-glacial landscape. The Shield. Archaic peoples left their traces in the archaeological record of the Hudson Bay lowlands in the form of stone tools, hearth features, and occasional burial sites. The preservation of these ancient sites is challenging in the Hudson Bay environment, where freeze-thaw cycles, waterlogged soils, and the growth and decay of peat are constantly working to obscure or destroy the archaeological record. But careful excavation at key sites has revealed a picture of well-adapted, mobile hunters who understood the rhythms of the northern ecosystem with an intimacy that comes only from generations of accumulated knowledge. Around 4,000 years ago, a new cultural tradition began to appear in the archaeological record of the eastern Hudson Bay region. This was the Dorset culture, the people who many archaeologists identify as the ancestors of the Inuit, though the relationship between the Dorset people and the later Inuit is a matter of ongoing scholarly debate. The Dorset culture was superbly adapted to the Arctic and subarctic environment. They developed sophisticated technologies for hunting marine mammals in and around sea ice, including specialized harpoons, small sleds, and forms of clothing and shelter that allowed them to live and travel in conditions that would be fatal to unprepared humans. The Dorset people occupied the coasts and islands of Hudson Bay for roughly 3,000 years, developing a distinctive artistic and material culture that is recognizable across a broad geographic area. Their small, exquisitely crafted carvings of animals, humans, and supernatural beings are among the most striking works of art produced in the prehistoric Arctic. They represent a cultural tradition of remarkable depth and sophistication, developed by people who lived in one of the most demanding environments on Earth and who had found ways to thrive there. Around 1,000 years ago, the Dorset culture began to be replaced by a new people, the Thule, who expanded eastward from Alaska across the Canadian Arctic with extraordinary speed. The Thule were the direct ancestors of the modern Inuit, and their expansion was driven by several factors, including superior technology, particularly the large skin boats called umiaks that allowed them to hunt bowhead whales, and possibly by a shift in climate conditions that temporarily favored their particular subsistence strategy. The relationship between the Thule and the Dorset is one of the most intriguing puzzles in the archaeology of the Arctic. Did they coexist for a period? Did the Thule displace the Dorset through competition, conflict, or both? Was there any cultural transmission between them, any borrowing of technologies or ideas? The archaeological record provides some evidence for all of these possibilities, and the debate among researchers continues. What is clear is that by approximately 500 years ago, the Dorset culture had disappeared from the archaeological record, and the Inuit, descendants of the Thule, occupied the coasts of northern Hudson Bay from Kivalliq on the western shore to Nunavik on the eastern shore, and on the southern and western shores, the Cree and Ojibwe peoples had developed their own sophisticated relationships with the bay and its resources, centered on the inland forests and wetlands rather than the open water and ice of the Inuit world. These were the peoples that European explorers encountered when they first pushed into Hudson Bay in the late 16th and early 17th centuries. And those European encounters, whatever their eventual consequences, began in a spirit of mutual curiosity and practical necessity that is often lost in the more dramatic telling of what came later. The European exploration of Hudson Bay is one of the great adventure stories of the age of exploration, and it is also one of the great tragedies. The driving motivation, as it was for virtually all European exploration of the Canadian North, was the search for a northwest passage, a navigable sea route through or around North America to Asia. The commercial logic was simple. If ships could reach Asia by sailing west and north from Europe, they would avoid the long and dangerous routes around the Cape of Good Hope or through the Ottoman-controlled lands of the Middle East. The profits to be made from Asian trade were enormous, and the incentive to find a shorter route was correspondingly powerful. Henry Hudson, the English navigator whose name the bay bears, was not the first European to enter its waters. That distinction belongs to earlier explorers, possibly including the Portuguese navigator Gaspar Corte Real in the early 16th century, though the historical evidence is ambiguous. But Hudson's voyages in 1610 and 1611 were the most consequential in terms of documenting the bay's geography and sparking intense European interest in the region. Hudson's final voyage ended in catastrophe. Having spent the winter of 1610 to 1611 in James Bay, the southern extension of Hudson Bay, Hudson's crew mutinied in June 1611. The captain, along with his son and 7 loyal crew members, was set adrift in a small open boat. They were never seen again. The mutineers returned to England with fragmentary charts and a story of a vast inland sea that captured the imagination of English merchants and adventurers. Subsequent expeditions to Hudson Bay in the decades following Hudson's disappearance confirm the broad outlines of his reports. The bay was enormous. The coasts were rich in wildlife. The indigenous peoples who lived there had access to furs, particularly beaver pelts, that were in high demand in Europe for the hat-making trade. And the possibility, however diminishing, of a northwest passage through or north of the bay continued to motivate exploration. In 1668, a small vessel called the Ketch Nonsuch sailed into Hudson Bay under the command of Zachariah Gillam, backed by a consortium of English merchants. The Nonsuch spent the winter in James Bay, trading for beaver pelts with the local Cree peoples, and returned to England in 1669 with a cargo of furs that demonstrated the commercial potential of the bay. 2 years later, in 1670, King Charles II of England granted a royal charter to the Governor and Company of Adventurers of England. Trading into Hudson's Bay, better known to history as the Hudson's Bay Company. The Hudson's Bay Company Charter was one of the most extraordinary documents in the history of European colonialism. It granted the company a monopoly on trade in all the lands draining into Hudson Bay, an area that would eventually be defined as nearly a third of the entire North American continent. The company was empowered to make laws, maintain a military force, and exercise sovereign powers in this vast territory, which it called Rupert's Land, after Prince Rupert, the first governor of the company. The establishment of the Hudson's Bay Company transformed the human geography of the Hudson Bay region. The company built trading posts, called factories, at strategic points around the bay's shore, beginning with Moose Factory on James Bay in 1673. Indigenous peoples, particularly the Cree, became integral to the company's trading network, providing furs in exchange for European goods, including metal tools, firearms, cloth, and food. This economic relationship was mutually beneficial in its early phases, though the balance of power and benefit would shift dramatically over the following centuries. The fur trade era, which lasted in its classic form from the late 17th to the mid-19th century, shaped the human geography of the Hudson Bay region in ways that are still visible today. The trading posts that the Hudson's Bay Company established became the nuclei of permanent settlements. The trading relationships that the company formed with indigenous peoples created new dependencies and new social structures, and the intense harvest of fur-bearing animals, particularly beaver, significantly altered the ecology of the region's waterways and wetlands. The story of the fur trade is also the story of the gradual European penetration of the continental interior. From the trading posts on Hudson Bay, company men and independent traders pushed inland along the river systems, mapping the country, establishing relationships with new indigenous groups, and extending the network of the commercial fur trade into regions that had previously been entirely outside the European sphere of knowledge. One of the most remarkable figures of this era was Samuel Hearne, a Hudson's Bay Company employee who became the first European to reach the Arctic Ocean. Overland from the east, traveling northward from Fort Prince of Wales on Hudson Bay to the mouth of the Coppermine River on the Arctic coast between 1769 and 1772. Hearne's journey, guided by the Dene leader at Matanabe, covered thousands of kilometers of entirely unmapped territory. His account of the journey, published in 1795, is one of the classic documents of northern exploration, combining detailed geographical observation with frank accounts of the indigenous cultures he encountered. Hearne's journey and the many other expeditions mounted by the Hudson's Bay Company and by naval explorers in search of the Northwest Passage gradually filled in the map of the Hudson Bay region. By the mid-19th century, the broad outlines of the bay's geography, its coastline, its major river systems, and the general character of the surrounding terrain were reasonably well understood. What remained mysterious, and what would remain mysterious for much longer, was what lay beneath the surface in the rocks and sediments and deep structure of the earth below. The scientific investigation of the Hudson Bay region's geology began in earnest in the 19th century as part of the broader enterprise of geological survey that accompanied the expansion of the Canadian state after Confederation in 1867. The Geological Survey of Canada, established in 1842, sent geologists into the field throughout the second half of the 19th century to map the rocks, identify mineral deposits, and understand the geological structure of the vast country. The Canadian Shield, and the Hudson Bay region specifically, presented particular challenges for 19th century geologists. The terrain was remote, accessible only by water and on foot. The climate was harsh. The winters were extreme, and the geological problems were formidable. The shield rocks were ancient, complex, and poorly understood by the geological science of the time, which was only beginning to develop the conceptual frameworks needed to interpret Precambrian geology. Nevertheless, the early geologists of the Geological Survey made remarkable progress. By the end of the 19th century, the broad outlines of the shield's geological structure were established. The immense age of the shield rocks was recognized, though the precise dates would have to wait for the development of radiometric dating in the 20th century. The existence of the ancient suture zones and crustal provinces was beginning to be dimly perceived, and the enormous mineral wealth of the shield in iron ore, copper, nickel, gold, and other metals was becoming apparent. The 20th century brought new tools and new questions to the geological investigation of Hudson Bay. The development of seismic reflection and refraction surveys, which use artificially generated seismic waves to probe the structure of the crust, allowed geologists to image the underground structure of the shield in increasing detail. Drilling programs provided rock samples from depth. Geochemical analysis of those samples allowed researchers to trace the history of the rocks and the fluids that had passed through them. And gradually, the complex geological history of the Hudson Bay region began to come into focus. The revelation of the gravitational anomaly over Hudson Bay and the subsequent debate about its causes became one of the central geological research questions of the latter 20th century. Satellite gravity measurements beginning in the 1970s and becoming increasingly precise in subsequent decades, provided the data that drove this debate, and the deployment of seismograph networks across Canada beginning in earnest in the 1980s and accelerating in the 1990s and 2000s produced the seismic tomography datasets that allowed researchers to image the mantle structure beneath the bay in 3 dimensions for the first time. What those images showed, and what the gravity data confirmed, was that the geological history of Hudson Bay could be read not just in the rocks at the surface, but in the deep structure of the earth beneath. The cold, dense keel of ancient lithosphere, the gravitational deficit, the ongoing rebound, all of these features were interconnected. All of them reflected the layered geological history of a region that had been shaped by processes operating over timescales stretching from the present day back to the very earliest history of the planet. There is a peculiar phenomenon that happens when you spend enough time thinking about the deep geological history of a place like Hudson Bay. The timescales involved begin to blur the distinction between past and present. You start to see the current landscape not as a fixed and stable thing, but as a single frame in a very long film. The polar bears on the ice are temporary. The ice itself is temporary. The bay is temporary in geological terms. Everything you see today is just one configuration of materials that have been rearranging themselves for billions of years and will continue to rearrange themselves long after any human observer is present to notice. This perspective is not nihilistic. It is, if anything, the opposite. It sharpens the appreciation for what exists right now in this particular moment of geological time, and it deepens the understanding of how the present configuration came to be. Because what exists beneath Hudson Bay and around it and in the waters of the bay itself is the result of an extraordinary sequence of events, each one building on the last, each one leaving its mark in the record that researchers are still learning to read. The water of Hudson Bay itself is a remarkable thing. It is not purely marine water in the way that the open ocean is. The bay receives enormous volumes of fresh water from the rivers that drain into it, the Churchill, the Nelson, the Severn, the Grande Rivière de la Baleine, and dozens of others. These rivers drain a catchment area of approximately 3.7 million square kilometers, one of the largest river catchments in North America. The freshwater input from these rivers creates a layered water column, with relatively fresh, less dense water near the surface, and saltier, denser water at depth. This stratification has profound effects on the bay's ecology, its ice formation, and its role in the broader North Atlantic climate system. The freshwater cap on the surface of the bay freezes more readily than fully saline ocean water, which is why Hudson Bay develops a nearly complete ice cover in winter, even though it is not particularly cold by Arctic standards. And the seasonal melting of this ice creates a pulse of cold, fresh meltwater into the marine system each spring, which affects the circulation of the broader North Atlantic. The ecology of Hudson Bay is structured around these physical and chemical conditions. At the base of the food web, phytoplankton, single-celled photosynthetic organisms, bloom in the surface waters during the brief Arctic summer, fueled by nutrients brought up by mixing and by the long daylight hours of the high-latitude summer. This phytoplankton bloom supports populations of zooplankton, small crustaceans and other invertebrates that graze on the phytoplankton. The zooplankton in turn support populations of fish, particularly Arctic cod and various species of char and whitefish, as well as the vast numbers of seabirds that breed along the Hudson Bay coast. The marine mammals of Hudson Bay are among the most charismatic and ecologically significant species in the system. Beluga whales congregate in the shallow estuaries of the major rivers during summer, in some cases in aggregations of thousands of individuals. Of these gatherings are one of the great wildlife spectacles of North America, drawing researchers and ecotourists to remote locations like the mouth of the Churchill River and the Seal River estuary. The belugas use the warm, shallow estuarine waters for molting, calving, and socializing, taking advantage of the brief summer window when the rivers are ice-free. Ringed seals are the most abundant marine mammals in the bay, present in very large numbers throughout the year. They are the primary prey of polar bears, and the distribution of ringed seals on the sea ice determines the distribution and foraging success of the bear population. The western Hudson Bay polar bear population, one of the most intensively studied polar bear populations in the world, is in serious decline. The population has dropped from approximately 1,200 animals in the 1980s to fewer than 800 today. The primary driver of this decline is the reduction in sea ice, which reduces the bears' hunting season and their ability to accumulate the fat reserves they need to survive the ice-free season on shore. The sea ice story on Hudson Bay is one of the most clearly documented indicators of climate change in Canada. The spring breakup date, the point at which the sea ice becomes too thin and fragmented for polar bears to walk on, has moved about 3 weeks earlier since the 1980s. The fall freeze-up date, when the ice becomes solid enough for bears to return to the seal hunting season, has moved about 2 to 3 weeks later. The result is that polar bears in western Hudson Bay spend several weeks more on shore fasting than they did 40 years ago. And the evidence that this is affecting their body condition, their reproductive success, and their survival rates is extensive and compelling. The situation is further complicated by the direct effects of warming on the permafrost in the Hudson Bay lowlands. As mentioned, the peatlands that blanket the lowland terrain around the southern and western shores of the bay are an enormous reservoir of carbon accumulated over thousands of years since the last glaciation. These peatlands support their own distinctive ecology, dominated by sedges, mosses, and the shrubs and small trees of the boreal and sub-boreal zones. They are critical habitat for migratory birds, for caribou, and for the numerous smaller mammals and insects that form the foundation of the food webs in this ecosystem. The warming of the permafrost is already visibly transforming the peatland landscape. The phenomenon known as thermokarst, where thawing permafrost causes the ground surface to collapse and subside, is creating new pools and ponds across the landscape. Drunken forests, where trees tilt at crazy angles because the permafrost that anchored their roots has thawed, are increasingly common, and in some areas the wholesale collapse of permafrost is converting former terrestrial peatlands into open water, releasing the stored carbon into the atmosphere at a rate that current models may significantly underestimate. The Hudson Bay lowlands are not the only peatland region in Canada that is experiencing this kind of transformation. Similar changes are occurring across the boreal and subarctic zones of the country. But the Hudson Bay lowlands are one of the largest and most carbon-rich of these regions, and their fate in a warming world matters enormously for the global carbon budget. Here is a number worth sitting with. The Hudson Bay lowlands contain an estimated 30 billion tons of carbon stored in their peat and permafrost. 30 billion tons. The entire global emission of carbon dioxide from all human activities, including all the coal, all the oil, all the gas burned anywhere in the world in a year, amounts to roughly 10 billion tons of carbon. The Hudson Bay lowlands contain 3 years' worth of current global carbon emissions, locked in the frozen organic matter of the peat. If warming releases a significant fraction of that carbon, over the coming century, the feedback effect on the global climate will be substantial. The researchers who study this are not alarmist by temperament. They are careful, methodical scientists who spend years collecting data and checking their results before publishing. And what they are finding is deeply concerning. The permafrost in the Hudson Bay lowlands is warming. The active layer, the portion of the soil that thaws in summer and refreezes in winter, is deepening. The carbon that is being released into the atmosphere from decomposing peat is increasing, and the model suggests that these trends will accelerate as warming continues. But here is the paradox that makes the Hudson Bay region's climate story particularly complex. The same warming that is thawing the permafrost and releasing carbon is also, in some areas, increasing the productivity of the remaining vegetation. Warmer temperatures and longer growing seasons are allowing shrubs and trees to colonize areas that were previously too cold for them. This shrubification and tree line advance represents an uptake of carbon from the atmosphere as the new vegetation grows. The net effect, whether the carbon released by permafrost thaw exceeds the carbon captured by new plant growth, is one of the central questions in the science of Arctic and subarctic carbon cycling. The answer, from what researchers have been able to determine so far, is that the carbon release from permafrost thaw is likely to significantly exceed the carbon captured by vegetation growth in the short to medium term, making the Hudson Bay region a net source of carbon to the atmosphere under most warming scenarios. But the uncertainty around this conclusion is substantial, and the research continues. Beyond the carbon cycle, the warming of the Hudson Bay region is altering the hydrological cycle in ways that are only beginning to be understood. The rivers that drain into the bay are changing in their timing and their volume. Spring floods driven by snowmelt are occurring earlier. The relative contribution of snowmelt versus rainfall to the river's flow is shifting, and the increased evaporation from the warming bay itself is altering precipitation patterns in the surrounding region. The communities that live around Hudson Bay are experiencing these changes directly. Churchill, Manitoba, the most accessible community on the western shore of the bay, has become a focal point for research into the environmental changes affecting the region. The town, with a population of roughly 900 people, is the only community in the world where polar bears, beluga whales, and Northern Lights tourism all coexist as economic drivers. It is also a community that has had to grapple directly with the consequences of climate change, including the disruption of traditional ice-dependent activities, changes in wildlife behavior, and the ongoing risks associated with a town built partly on thawing permafrost. The indigenous communities of the Hudson Bay region, the Cree of the southern shores, the Ojibwe of the far south, the Inuit of the northern coasts and islands, are navigating the most rapid environmental change these lands have experienced in thousands of years. The land and the bay are central to indigenous cultural identity, spiritual life, and subsistence practice in ways that are difficult to fully convey to those who have not lived in this relationship. When the sea ice changes, when the caribou migrations shift, when the fish populations move, when the berry crops fail, the consequences are not just economic. They are cultural and spiritual. The documentation of traditional ecological knowledge, the accumulated understanding of the Hudson Bay environment that indigenous peoples have developed over thousands of years of observation and interaction, has become an increasingly important component of the scientific research program in the region. Researchers have come to recognize that the knowledge systems of indigenous peoples contain information that scientific monitoring programs have only recently begun to collect, going back decades, or in some cases generations. The integration of this knowledge with the data produced by scientific monitoring is one of the most productive and promising developments in Hudson Bay research. The federal and provincial research programs focused on Hudson Bay have expanded significantly in recent decades, driven by both scientific curiosity and the practical urgency of understanding how the region is changing. Projects like the Bay-SIS program, a major multi-institution research initiative that studied the Hudson Bay system comprehensively from 2016 to 2021, have produced an enormous volume of new data on the physics, chemistry, biology, and ecology of the bay and its surrounding landscape. What that data reveals is a system in rapid transition. The physical environment is changing faster than the biological communities can fully adapt. The policy and governance frameworks that manage the bay's resources are struggling to keep pace with the pace of environmental change. And the communities that depend on the bay, both human and wildlife, are caught in the middle of a transformation that has no historical precedent in the timescales relevant to human experience. The deep geological history of Hudson Bay, the ancient rocks, the fossil mountain roots, the gravitational anomaly, the long record of glaciation and deglaciation, all of this provides essential context for understanding the current moment. The bay has been through changes before, dramatic, catastrophic changes by any reasonable standard. The Ordovician extinction killed most of the marine life in the oceans. The glaciations buried the bay under kilometers of ice. The Lake Agassiz outburst triggered a global climate event, and each time, eventually, life recovered, adapted, found new forms and new strategies for existence in the changed world. But the pace of the current changes is what distinguishes them from the geological changes of the past. The glaciations came and went over thousands of years. The Ordovician extinction, though geologically abrupt, played out over thousands to tens of thousands of years. The current warming of the Hudson Bay region is happening over decades. The permafrost is thawing in years. The sea ice is changing within the lifetime of a single polar bear. Ecosystems can adapt to gradual change. They have much more difficulty with change that happens faster than evolutionary processes can respond to. And the current rate of change in the Hudson Bay region is, in many respects, faster than anything recorded in the geological past at this latitude. There is a research station in Churchill, Manitoba, that has been continuously monitoring the Hudson Bay environment for decades. The Churchill Northern Studies Center, established in 1976, sits on the western shore of the bay at the edge of the boreal forest, where the trees give way to the open, windswept tundra that extends northward toward the Arctic coast. From this facility, researchers have studied polar bears, beluga whales, migratory birds, permafrost, sea ice, atmospheric chemistry, and dozens of other aspects of the Hudson Bay system. The data accumulated over nearly 5 decades of continuous monitoring is one of the most comprehensive records of environmental change in the subarctic world. What that data shows, across all the different systems being monitored, is consistent with a single overarching narrative. The Hudson Bay region is changing, and it is changing fast. The question that occupies the researchers who work with that data is not whether the changes are real, they manifestly are, but what the consequences will be, how they will propagate through the ecological and social systems of the region, and what, if anything, can be done to understand and respond to them. But alongside the immediate and urgent questions of environmental change, there are deeper questions that continue to drive the geological and geophysical research. Questions about what the Hudson Bay region can tell us about the fundamental processes that shape the Earth's interior and surface. Questions about the relationship between the deep geological structure and the surface processes that we can observe and measure. Questions about how the Earth records its own history in the structure of the crust and the mantle, and how we can learn to read that record. The investigation of the gravitational anomaly over Hudson Bay, which began in earnest in the 1960s and has continued to the present day, is a good example of how these questions drive research. The anomaly is real, measurable, and well documented. The basic explanation that it reflects a combination of post-glacial rebound and the presence of ancient, cold, dense mantle material beneath the bay is broadly accepted, but the details are still being worked out, and each new data set adds nuance to the picture. One of the most significant recent developments in the study of the Hudson Bay mantle has been the improvement in seismic tomography from the Polaris and other Canadian seismograph networks deployed across the Canadian Shield. These networks have produced high-resolution images of the mantle structure beneath the shield, revealing the detailed geometry of the lithospheric keel and the complex structure of the transition zone between the old, stable Creighton root and the more recently mobilized mantle beneath it. These images have shown that the lithospheric keel beneath the Hudson Bay region is not a simple, uniform block. It has internal structure. There are regions within it that appear to correspond to the boundaries between the ancient crustal blocks that were assembled during the trans-Hudson origin. The superior Creighton root, the Churchill Province root, and the trans-Hudson suture zone itself all appear to have distinct signatures in the seismic tomography, suggesting that the deep structure of the lithospheric keel preserves the record of the ancient tectonic assembly at depths of 100 kilometers or more below the surface. This is a remarkable finding. It means that the lithosphere, far from being a simple, featureless layer, preserves the detailed structural imprint of tectonic events that happened nearly 2 billion years ago. The ancient suture zone that is visible in the surface rocks of the Canadian Shield continues downward into the deep lithosphere, stamped into the fabric of the Earth itself by the force of the trans-Hudson collision. And it has persisted there, essentially unchanged through all the glaciations, all the erosion, all the surface changes of the past 2 billion years. This kind of preservation of ancient tectonic structure in the deep lithosphere is not unique to the Hudson Bay region. Researchers have found similar patterns beneath other ancient cratons around the world. But the Hudson Bay case is particularly well documented because of the density of the seismograph network, the extensive geological mapping of the surface rocks, and the decades of gravity and other geophysical measurements that provide complementary constraints on the deep structure. The picture that emerges from all of this research is one of the clearest examples anywhere on Earth of what geologists call the deep lithospheric architecture of an ancient continent. The surface geology of the Canadian Shield, the rocks you can pick up and examine with a hand lens, reflects the processes that operated at or near the surface in the ancient past. The geophysics of the deep structure, the seismic tomography, the gravity data, the rebound rates, reflects the processes that operated at depth in the mantle and the deep crust over the same period of geological history. Together, they tell a story that is far more complete than either line of evidence alone. And that story, read from top to bottom, from the permafrost at the surface down through the sediments, through the ancient shield rocks, through the deep lithosphere, into the cold mantle root 200 kilometers below, is the most complete geological biography of any region of Canada, possibly of any region of North America. The story begins with the formation of the Archean crust more than 3 billion years ago, in an era when the Earth's interior was hotter and more vigorous than it is today. The ancient volcanic rocks and sediments of the earliest shield record, a world of intense geological activity, of rapidly cycling oceanic crust, and the first hesitant formation of stable continental blocks. These are the oldest materials in the story, the original pages of the geological record of the Hudson Bay region. Then comes the Great Oxidation Event, 2.4 billion years ago, recorded in the banded iron formations of the Shield, the chemical signature of a biological revolution that transformed the chemistry of the planet. The cyanobacteria that drove this transformation were the most consequential organisms in the history of the Earth in terms of their impact on the planetary environment, and the rocks of the Hudson Bay region preserve their handiwork in the form of economically valuable iron ore deposits that continue to be mined today. Then the trans-Hudson origin, 1.9 to 1.8 billion years ago, the collision of ancient cratons that assembled the central Canadian shield and drove mountains of Himalayan scale above what is now the Hudson Bay region. The root of those mountains, cold and dense, still sits in the mantle beneath the bay. The suture zone of the ancient collision is still visible in the surface rocks and in the deep seismic tomography. This is the most enduring geological legacy of the Hudson Bay region, the feature that has shaped its gravitational field and its deep structure for nearly 2 billion years. Then the long quiet of the mid-Proterozoic and early Paleozoic, as the ancient shield eroded slowly under the atmosphere and the ancient oceans advanced and retreated across it repeatedly. The sedimentary rocks laid down in these ancient seas, the carbonates and shales and sandstones of the Ordovician, Silurian, and Devonian periods, now preserved in the Hudson Bay lowlands and on the floor of the bay itself, record the biological story of the Paleozoic oceans, including the catastrophic Ordovician extinction that killed 85% of marine species and set the course of animal evolution on a new trajectory. Then the dramatic cycles of the Quaternary, the repeated advance and retreat of ice sheets that scoured the shield, carved the landscape, pressed the crust down into the mantle, and melted to produce the lakes and rivers and bogs and wetlands that characterize the Hudson Bay region today. The Lake Agassiz outburst flood, the Younger Dryas cooling, the post-glacial rebound that continues to the present day, still raising the land at rates measurable with modern GPS equipment. Then the arrival of human beings, the shield archaic hunters following caribou into the newly deglaciated landscape, the Dorset people adapting their extraordinary ice hunting culture to the shores of the bay, the Thule expanding rapidly across the Arctic and eventually becoming the Inuit, the Cree and Ojibwe developing their deep relationships with the forest and water ecosystems of the southern shores, and then the Europeans, the fur traders, the company men, the explorers seeking the Northwest Passage, the scientists and researchers who began to probe the geological depths of the region in the 19th and 20th centuries. And now the present, with its urgency and its complexity, the warming climate, the thawing permafrost, the retreating sea ice, the declining polar bear population, the changing beluga whale population dynamics, the shifting vegetation zones, the communities trying to adapt to a world that is changing faster than any of them have experienced before. All of this unfolding above the same ancient rocks, the same deep cold mantle root, the same gravitational anomaly that has been a feature of this piece of the planet for nearly 2 billion years. The connection between these different layers of the story is not merely geographic. They are connected by the principle that what has happened in the past shapes the conditions of the present. The ancient tectonic history of the Hudson Bay region created the geological conditions, the stable craton, the low-lying terrain, the position in the interior of the continent that made it the nucleation point for the great ice sheets of the Quaternary. The glaciations created the landscape and the soils that allowed the post-glacial peatlands to develop. The peatlands created the carbon reservoir that now sits, potentially unstable, in the warming climate. The warming climate is triggering changes that are affecting the ecology, the hydrology, and the communities of the region in ways that cascade through all of these systems simultaneously. This kind of deep time perspective, seeing the present as the outcome of billions of years of geological and biological and cultural history, is one of the most powerful tools available for understanding why the world is the way it is. And Hudson Bay is one of the places where this perspective is most richly rewarded, because the record is so complete, the layers so clearly preserved, the connections between deep time and the present so traceable. Consider for a moment the chain of causation that connects the trans-Hudson origin to the polar bears of today. The collision of ancient cratons nearly 2 billion years ago created a deep, cold, lithospheric keel beneath the Hudson Bay region. That keel stabilized the ancient crust, preventing it from being deformed and recycled by the geological processes that have transformed much of the rest of the planet's surface. The stable, ancient crust persisted through subsequent geological eras, providing the resistant basement on which the later sedimentary rocks were deposited and the glaciations worked. The position of the region in the interior of North America, partially a consequence of the ancient tectonic history, made it the natural center of the great Laurentide ice sheet of the Quaternary. The ice sheet created the landscape, the shallow bowl-shaped terrain that became Hudson Bay when the ice melted. The bay's geography, surrounded by flat, low-lying terrain and connected to the subarctic climate of the Hudson Bay lowlands, created ideal conditions for the formation of sea ice in winter. And the sea ice supports the ring seal populations that the polar bears depend on. Remove the trans-Hudson origin 2 billion years ago, and through that chain of consequences, you remove the polar bears today. The connection is indirect, mediated through billions of years of geological and evolutionary history, but it is real. The present is the outcome of the past, all the way down to the deepest geological past. This is what scientists mean when they talk about the Hudson Bay region as a place where you can read the deep history of the Earth. It is not just a collection of interesting geological features. It is a narrative, a continuous story told in rock and ice and water and life, running from the Archean basement to the warming present. And the thing that is sealed beneath the bay, the ancient cold mantle root of the trans-Hudson Mountains, is the oldest and deepest sentence in that narrative, written in the fabric of the earth itself nearly 2 billion years ago. The research continues. New generations of geologists, geophysicists, ecologists, climatologists, and oceanographers are adding new pages to this story every year. The seismograph networks are being expanded and upgraded. The satellite gravity measurements are becoming more precise. The drilling programs in the Hudson Bay lowlands are recovering new sediment cores that extend the paleoclimate record further back in time. The long-term environmental monitoring at Churchill and other stations is accumulating data that will take decades to fully analyze and interpret. And the indigenous communities of the Hudson Bay region are contributing their own knowledge and perspectives to this growing understanding. The land use and occupancy studies, the traditional ecological knowledge documentation projects, the collaborative research programs that bring indigenous knowledge, keepers and academic scientists together are producing insights that neither group could achieve alone. The knowledge that comes from living with a landscape for thousands of years, from paying close attention to its rhythms and changes across generations, complements the knowledge produced by scientific instruments in ways that are only beginning to be fully appreciated. The future of Hudson Bay, like its past, will be shaped by the interaction of forces operating across a vast range of scales. The deep geological forces, slow and ancient and enormously powerful, will continue to operate regardless of anything that happens at the surface. The rebound will continue. The cold mantle root will persist. The gravitational anomaly will remain a feature of this piece of the planet for geological time to come. The surface forces, the climate, the ice, the ocean circulation, the ecology, are more immediately responsive to human actions. whether the warming continues at its current rate or accelerates, whether the sea ice disappears entirely from Hudson Bay in summer within decades or maintains some seasonal presence for longer, whether the permafrost thaws rapidly and releases enormous quantities of carbon, or thaws more slowly, with somewhat less dramatic consequences. All of these outcomes depend to a significant degree on choices being made right now by governments, corporations, and individual people around the world. The communities of the Hudson Bay region will live with the consequences of those choices. The polar bears will live with them or not. The beluga whales will adapt or not. The peatlands will continue to accumulate carbon or will begin releasing it at scale. The answer to these questions will be written in the coming decades in the ongoing story of one of the most geologically, ecologically, and culturally significant places in Canada. But beneath it all, sealed under the cold water of the bay and the ancient rock of the Canadian Shield, the deep geological record will persist. The mantle root of the Trans-Hudson Mountains will continue to sit there, cold and dense and ancient as it has for nearly 2 billion years, as it will for billions more. The gravitational anomaly will continue to pull at the instruments of the scientists who measure it. The rebound will continue, centimeter by centimeter, year by year, the Earth slowly recovering from the most recent of the many great ice sheets that have pressed upon it through geological time. And somewhere in the rocks at the bottom of Hudson Bay, in the Ordovician, sediments laid down when the bay was a tropical sea, in the banded iron formations recording the great oxidation event, in the ancient Archean basement below them all, the full record of what this place has been and what it has witnessed across geological time is preserved, waiting for the researchers who will eventually learn to read all of its pages. The thing sealed beneath Hudson Bay has been there for thousands of years, as the title of this story suggests. But the truth is even stranger and more extraordinary than that framing captures. It has been there for millions of years, for hundreds of millions of years, for nearly 2 billion years, since before complex life existed anywhere on the planet, since before the continents took their current form, since before the atmosphere had oxygen enough for an animal to breathe. Hudson Bay, the cold, beautiful, troubled body of water in the heart of Canada, is sitting on top of one of the oldest and most deeply preserved geological features on the surface of the earth, a remnant of an ancient mountain system sealed in the cold mantle, a record of the oldest tectonic events in the history of the continent, a window into a deep time that dwarfs all of human history, all of recorded civilization, all of the time since the first cell divided and the first organism drew energy from its chemical surroundings. The next time you see Hudson Bay on a map, it is worth pausing for a moment to consider what lies beneath it. Not the immediate beneath, not the water and the sediments and the ancient rock surface at the bottom of the bay, but the deep beneath, the lithospheric keel 200 kilometers down, the cold mantle root of mountains that no longer exist, the gravitational anomaly that still, right now, bends the fabric of space-time over this extraordinary piece of the planet. It has been there for a very long time. It will be there for a very long time to come. And we are only beginning to understand what it can tell us about the deep history of the world we live on. There is a dimension of the Hudson Bay story that has not yet been fully told, and it belongs to the scientists themselves. The men and women who have devoted careers to understanding this region, who have spent weeks on research vessels in the frigid waters of the bay, who have lowered instruments through ice, augured in minus 40-degree temperatures, who have crawled through bogs and tundra collecting samples, who have stared at seismic tomography images trying to make sense of the shadows and bright spots that represent the Earth's interior. Their story is also part of what makes Hudson Bay remarkable, because the scientific Investigation of the bay has been in many ways a microcosm of the broader development of earth science as a discipline over the past century. In the early decades of the 20th century, the tools available for investigating the deep structure of the Hudson Bay region were primitive by modern standards. Geologists could map the surface rocks with care and precision, noting their composition, their structure, their age relationships. But the subsurface was largely inaccessible. The only direct samples from depth came from mining operations, where diamond drilling extended a few kilometers into the crust, and these provided invaluable information about the local geology but could not reveal the regional picture. The development of seismic reflection profiling after the Second World War changed the situation dramatically. Originally developed by the petroleum industry for exploring sedimentary basins for oil and gas, seismic reflection techniques were adapted by academic researchers for studying the deep crust and upper mantle. A seismic reflection survey works by generating a controlled seismic source, originally dynamite explosions, more recently large vibrating trucks or air guns in marine settings, and recording the waves that bounce back from different layers within the earth. By carefully analyzing the timing and character of these reflected waves, researchers can construct images of the subsurface structure to depths of tens of kilometers. The Lithoprobe program, a major Canadian geoscience initiative that ran from 1984 to 2003, applied seismic reflection and other geophysical methods to the systematic study of the deep structure of the Canadian crust, including the Hudson Bay region. Lithoprobe was a landmark achievement in Canadian science. It brought together hundreds of researchers from universities and government agencies across the country, deployed state-of-the-art geophysical instruments across an enormous range of geological settings, and produced a body of knowledge about the deep structure of Canada's crust that transformed understanding of the country's geological history. The lithoprobe surveys in the Hudson Bay region, particularly the Trans-Hudson Origin Transect, image the deep crust along profile lines that cross the ancient suture zone and the surrounding cratons. The results were extraordinary. The seismic images showed the deep structure of the Trans-Hudson collision zone in remarkable detail, with reflective surfaces deep in the crust that corresponded to the ancient thrust faults along which the Superior and Churchill cratons had been forced together nearly 2 billion years ago. The route of the collision zone extended deep into the crust and was visible in the seismic images as a complex zone of reflections at depths of 30 to 50 kilometers. These images were the first direct glimpse of the deep architecture of one of the most ancient tectonic events in Canadian history. They confirmed what the surface geology had suggested, that the Trans-Hudson origin was a major collisional event of the same scale and character as the modern Himalayan collision, but they also revealed structural details that had never been imagined from the surface geology alone. The deep crust of the Trans-Hudson suture zone turned out to be complex, with multiple generations of thrusting and deformation superimposed on each other, reflecting the multi-stage nature of the collision between the ancient cratons. The lithoprobe results fed directly into the broader debate about the gravitational anomaly over Hudson Bay. The seismic images of the deep crust provided constraints on the thickness and structure of the crust in the Bay region, which in turn affected the models used to interpret the gravity data. The combined dataset, seismic images plus gravity data plus surface geology, allowed researchers to construct more sophisticated models of the deep structure than any of the individual datasets could support alone. What emerged from this combination was a picture of extraordinary geological complexity. The Hudson Bay region sits at the intersection of multiple ancient tectonic boundaries: the Trans-Hudson Suture Zone, the southern margin of the Churchill Province, the northern margin of the Superior Craton. Each of these boundaries has a distinct expression in the deep geology, and each contributes to the unusual geophysical character of the Bay region. The gravitational anomaly is not simply the result of a single ancient event. It is the cumulative expression of nearly 2 billion years of tectonic history, each chapter adding its contribution to the deep structure that is visible in the geophysical data today. The development of GPS geodesy in the 1990s added yet another dimension to the investigation of the Hudson Bay region. GPS satellites can measure the precise position of a point on the Earth's surface with an accuracy of a few millimeters. By deploying GPS receivers at fixed monuments across the Hudson Bay region and monitoring their positions continuously, over years and decades, researchers can measure the ongoing post-glacial rebound of the crust with extraordinary precision. The results of these GPS measurements have been fascinating. The land is indeed rising, at rates of up to 10 millimeters per year in some parts of the Hudson Bay region. But the pattern of rebound is not simple. Different parts of the region are rising at different rates, reflecting the complex geometry of the ice sheet that pressed the crust down and the complex viscosity structure of the mantle that is flowing back in as the crust rebounds. The GPS data provides a detailed picture of the rebound that can be used to constrain the viscosity of the mantle beneath the bay, providing yet another window into the deep structure of the Earth's interior in this region. The mantle viscosity derived from the rebound data is consistent with the picture from the seismic tomography. The mantle beneath the Hudson Bay region is cold and relatively stiff, consistent with the presence of the ancient, cold, lithospheric keel imaged in the tomography. The rebound is happening slowly because the mantle is viscous, and the mantle is viscous because it is cold, and it is cold because the ancient lithospheric root has been insulating the upper mantle from the heat of the deeper earth for nearly 2 billion years. Every line of evidence converges on the same conclusion. What lies beneath Hudson Bay is ancient, cold, and extraordinarily well preserved. It is one of the most complete examples of an ancient lithospheric root anywhere on the surface of the Earth, and it has been sitting there, shaping the geophysical character of the region above it, from before the first oxygen-breathing organism existed on the planet. The oceanographic research on Hudson Bay itself has its own remarkable history. The bay is surprisingly poorly known oceanographically, given its enormous size and its importance for the regional and potentially global climate system. Its remote location, the extreme difficulty of working in its icy waters for much of the year, and the practical challenges of operating research vessels in a region with limited port infrastructure have all contributed to a historical deficit in oceanographic knowledge. The Hudson Bay Project, which ran in the 1980s and early 1990s and involved research ships from Canada, the United States, and other countries, produced the first systematic oceanographic survey of the bay. The data collected during that project established the basic physical and chemical oceanography of the bay, documenting the stratification of the water column, the circulation patterns, the seasonal cycle of sea ice formation and melt, and the distribution of nutrients and biological production. But the Hudson Bay Project data was collected at a specific moment in time, before the full magnitude of climate-driven change in the bay had become apparent. The BASIS project, which ran from 2016 to 2021 and was led by the University of Manitoba, represented a major updating and expansion of the oceanographic knowledge base for the bay. BASIS deployed autonomous instruments in the bay throughout the ice season, a technically challenging achievement that required careful planning and some innovative engineering solutions. The autonomous instruments collected data on temperature, salinity, currents, and ice conditions through the winter when crewed research vessels cannot operate in the bay. The BASIS data revealed a bay that was changing in detailed and complex ways. The freshwater input from rivers was increasing in some seasons, altering the stratification of the water column and affecting the timing and character of the sea ice cycle. The ocean heat content was increasing. The biological productivity of the bay was shifting in response to the changing physical environment, with implications for the food webs that support the bay's marine mammals and seabirds. One of the most striking findings from the Bay SIS project was the documentation of how changes in the sea ice cycle were cascading through the food web of the bay. The timing of ice breakup affects when the phytoplankton bloom occurs, which affects when the zooplankton that feed on the phytoplankton are available, which affects the timing of arrival of migratory seabirds that come to the bay to breed and feed. If the bloom occurs earlier than the seabirds arrive, or if the zooplankton peak before the seabirds are ready to feed their chicks, the reproductive success of the seabirds declines. These kinds of phenological mismatches, disruptions in the carefully co-evolved timing of ecological processes, are among the most insidious consequences of rapid climate change in high-latitude ecosystems. The Hudson Bay marine ecosystem is not the only system experiencing these mismatches. They are being documented in Arctic and subarctic marine ecosystems around the world, but Hudson Bay, because of its long history of research and monitoring, provides some of the best documented examples of these phenomena, and the data from the bay is therefore unusually valuable for understanding the broader patterns of climate-driven ecological change. The question of what the future holds for Hudson Bay is one that researchers approach with a combination of scientific rigor and genuine concern. The scientific evidence for the direction of change is clear. The bay will continue to warm. The sea ice season will continue to shorten. The permafrost will continue to thaw. The peat carbon will continue to be mobilized. The consequences for the bay's ecology will continue to unfold. The communities that depend on the bay will continue to face challenges that are unprecedented in their recent history. What is less clear is the rate of these changes, the thresholds at which qualitative shifts in the system might occur, and the extent to which the consequences can be mitigated by actions taken at local, regional, national, and global scales. These are questions that require both the best available science and the engagement of the communities most directly affected, and increasingly, the research programs focused on Hudson Bay are designed to address both dimensions simultaneously. The story of what lies beneath Hudson Bay in all its layered complexity, from the ancient mantle route to the thawing permafrost to the changing sea ice, is ultimately a story about connection across scales, from the subatomic to the planetary, connection across time, from the Archean to the Anthropocene, connection between the physical world and the living world, connection between the human communities that inhabit this region and the natural systems that have sustained them for thousands of years. Understanding those connections, reading the record of the past with sufficient care and depth to make sense of the present and project intelligently into the future, is the central challenge of earth science in the 21st century. And Hudson Bay, with its extraordinary geological history, its deep and readable record, its urgent environmental challenges, and its remarkable communities of researchers, indigenous knowledge keepers, and people who live with the bay every day, is one of the places where that challenge is most clearly defined and most actively being met. What is sealed beneath Hudson Bay has been there for thousands of years, as this story began by saying. But more accurately, more truly, and more remarkably, it has been there for nearly 2 billion years. It is as old as any feature we can identify in the structure of the North American continent. It is as ancient as the oxygen in the atmosphere. It is older than any animal that has ever lived on Earth, and it is still there, still influencing the gravity above it, still shaping the rebound of the crust, still sitting in cold stability in the deep mantle beneath the cold, beautiful, rapidly changing bay that has been at the heart of one of the greatest geological, ecological, and human stories on the surface of this planet.